Unlike a standard statistics introductory course, this course, the goal is not to do statistical computations, it's to understand what the statistical computations tell you. And so now I think it's necessary to do some computations in order to really get a handle on it. But again, the major goal of a course like this is to be able to read and understand statistics. So with that in mind, I have some examples of articles from journals. These are medical journals, in fact, which I took out of our library. And so if you're taking the course, I will email you copies of this so you can follow along discussions. So hopefully you've got your copy of this stuff. And the first page is page 1671 from the, I think it's New England Journal of Medicine. And I don't recall what, 1995. And it's titled Granulocyte, the macrophage colony stimulating factor after initial chemotherapy for elderly patients with primary acute myelogenous leukemia. Alright, so that's, I don't have a whole lot of idea what that means. Okay, I'm a mathematician, not a nurse or a doctor. Well, this first article here, the beginning of the article has an abstract. This is a peer-reviewed article in a major medical journal, New England Journal of Medicine. And peer-reviewed means that people in the profession have reviewed the entire article for, methods, what they used, some accuracy, things like that. All right, so these articles typically have an abstract which summarizes the results of the study. And now if you look in the upper right part, you'll see some p-values. So this is in the results section, results conclusion section. And if you look closely there, they have near the top there, they have confidence intervals. 95% confidence intervals are given with these numbers, and they have p-values. So it's very typical to see a lot of p-values in a journal article like this. And now they don't show you all the calculations like we did. They don't write out hypothesis tests. They expect you to realize that a p-value tells you whether the comparison being done is significant or not, whether results are statistically significant or not. And it's more of a modern type of approach to hypothesis testing when they just give you the p-values and let you decide what is significant. So if for example, if a certain treatment, medical treatment, had a lot of great risk attached to it, a lot of high risk attached to it, then you may be looking for a very small p-value because you don't want to take the risk. You want to make sure the results are going to be significant. So anyway, but generally most people use 0.05 as their rule of thumb for rejecting or failing to reject a null hypothesis, or in plainer English, whether the comparison being made is statistically significant or not significant. All right. Well, so anyway, you see some confidence intervals and p-values listed there. Things you've been working on the past two chapters. Let's go on to the second page. And the only reason I copied this page is that it has a methods, big methods section in rather small print. And typically, peer-reviewed articles that involve statistics will explain the methodology used in the experiment. So this is, the really is scientific stuff. Here's how they conducted the experiment. Here's what statistics they used on it. And that's reviewed closely to make sure that the statistics is very good. They're really getting really true random samples, that the conclusions are appropriate for the way they collected the data and processed them. So methodology, it be kind of painstaking to read through that, but anyway, that's what that is. All right, page 3. And there's a chart on page 3. And table 1, upper right corner, reads characteristics of the patients at study entry. And there are three columns here. There's the GM-CSF column. That's the experimental treatment they're testing. And then the second column is the placebo column. And placebo means that the people in the study who got the placebo got basically a sugar pill and thought they were getting the drug. And so they're the control group being compared to the experimental GM-CSF group. All right, and then the last column is totals. So you can say that, okay, if you look at age group, which is about the second or so line down there, age group dash number, and then parentheses it says percentage, 60 to 69 years. So in the GM-CSF group, there were 95 people in that age group, which made up 49% of the total, and of the age group in the GM-CSF. So 49% in GM-CSF were 60 to 69. Okay, and you can read across there. So it has basically sample sizes and percent of total. That sample size is. That's all it is. And it shows all that stuff down here. All right, well, that's pretty much that. You'll find some confidence intervals and p-values buried in the text of the article here also. And there's a statistical analysis section also, which explains the statistics methodology. Page 4, which is actually page 1674. There are two charts on this, and the charts are called logistic regressions. And so a logistic regression tends to resemble this ogive curve. And you see this in various areas. For example, if you were studying the learning curve starts here and goes up and levels off. If you're studying the spread of an epidemic, it would tend to follow a logistic curve if there was no intervention. And because few people have the disease at the beginning, but then it picks up steam, and then when there are few people left to get the disease, the number tapers off. All right, so logistic regression is good for a couple of things. And so they processed this data and did some charts. So we don't study logistic regression in this course, but you can still kind of understand the statistics here. So if you look at the bottom left chart down here, it plots out the duration of neutropenia in days versus the proportion of patients. And the two curves are pretty close together. One is the placebo curve, one is the experimental curve, GM-CSF curve. Now, they're very close together. Are they statistically different or not? And if you look in the chart here, it has a p-value of 0.02, which is what? It's a small p-value. That tells us that the difference between the two groups, placebo and GM-CSF, the difference is significant. So now it looks going to be deceiving because it looks like those graphs are quite close to each other, but statistically there's a difference there. Now they also have something else, chi-square, and sometimes you'll see chi-square written this way. That's the Greek letter chi. Kind of looks like a stretched out X, but it's also chi. Chi-squared is 5.28 with 1 degree of freedom. We don't really do much with chi-square in this course. I'll touch on it in chapter 9 at the very end of the course. I'll touch on it, but by the time you learn chapter 10 and 11, chapter 9 is just more redundancy. But chi-square is a type of statistical distribution, and that compares actually two categorical variables together. This will make more sense when we talk about it in later chapters. So let's don't worry about chi-squared, 1 degree of freedom, what that means right now.